simply just substitute in the limits now. So 4 and 0. And once you substitute in the limit, you get 12 square units. So now let's have a look at these two curves. So the area we're looking for here is the region R. So we have a function f of x, which is sine 2x, and g of x, sine x, cos squared x. And we're looking to find the area between 0 and pi over 2. So to find the area, first of all, because the curves are already drawn out, we could just see the f of x has the greater area. So if we do f of x minus g of x, and then substitute in what f of x, g of x. So cos 2x, we know differentiates to minus 2 sine 2x. So we could do this, sine 2x, which is not a problem. And then we also look at cos cubed x, differentiation of that. So cos cubed x, when you differentiate, you bring the power down, so that's 3 cos squared x, times by cos x. Cos x gives you, differentiation of cos x gives you sine x. So we get the following. So this is all from reverse integration, which we would have met in the previous chapter. So now what we do is substitute this information in there. So we say the integration of sine 2x minus sine x cos squared x, it gives you the following. And we simply just substitute in the limits, which is pi over 2 and 0. So once we substitute the limits, we get 2 over 3. So sometimes the functions are very difficult to integrate, or at some other times it's actually impossible, certain functions to integrate. So in maths we have another way of solving this. It's called the numerical solution. And numerical solution is simply an approximation. And one of the approximation we're going to use today is called the trapezium rule. So suppose we have a curve that looks something like this, and we're interested in finding the area between A and B. We could split up the area into certain sections, and we have to make sure that each strip is of the same length, and we'll call that length h. And if I connect up each of the strips with a curve, I should get a set of trapezium. Hence this name comes as a trapezium rule. So now if I was to say I'm making this strip smaller, I will have more trapezium, and this time if you look at the curve, we should have a better approximation. So if you take more trapezia, then you get a better approximation to the equation. So if we just take this 3 trapezium for now, so first y coordinate, we'll call it y0, and then once we substitute in the other x value, we'll get the y coordinate, we'll call it y1. So we know the area of a trapezium is the sum of the parallel sides, and then you half it and times it by height. So in this case, your trapezium is facing the other way around. Your parallel sides are y0 and y1, and your perpendicular height is the h. So if we substitute that into the trapezium formula, we get the following. And if we do the same with the next trapezium, so we're going from y1 to y2, we get the area of trapezium as follows, and so on with the third one. So now the total area is a sum of all 3 trapezium. So if we add these up, we get the following. So we could tidy these up by taking a common factor of half h. So there's half h in all 3 of them. And now you see there's actually y1, y1 twice, y2, y2 twice. So we could further simplify this by putting a square bracket, writing half h, y0 plus 2 lots of y1 plus y2 plus